Alright, so you've given it your best shot in making an ice cream scoop contingency table. So now I will demonstrate how the correct way that this was done, and hopefully yours looks like mine. So clear out our dice contingency table. So the first thing is to get a handle on what are the different options for the rows and the columns. So I'm going to describe that as first scoop and second scoop. So there are, on the rows we're going to have the first scoop options, and on the columns we're going to have the second scoop. So options in first scoop are vanilla, chocolate, strawberry, and blue moon. Okay. Now the second scoop, we have vanilla, chocolate, strawberry, and blue moon. Okay. So if you think about this, there's 4 possible first scoops and there's 4 possible second scoops. And so if we combine all of these, we're going to get 16 possible cones. But what's going to be true about these 16 cones? These 16 cones are all 2 scoop cones, right? This is a vanilla cone, this is a chocolate vanilla cone, this is a vanilla chocolate cone. So we've got 16 possibilities, but they're all 2 scoop cones. And the problem specifically stated that you can serve 1 or 2 scoop cones. So how can we use this table as we've built it to incorporate the idea of 1 scoop cones? Well, what is true about the second scoop if it's a 1 scoop cone? Well, the answer is that there is a 5th flavor, so to speak, of second scoop, and it is the none flavor. So if we have no second scoop, that is also an option. So in the end, we have, assuming equally likely, all of these different possibilities. And we can get our row and column totals. So I'm using the sum function here in Excel. So I'll sum these. And then notice that the sum of the row sums and the sum of the column sums both add up to 20. So we have 20 possible cones, each of which are equally likely. And now we can start asking some simple probability questions. So we were asked, if every option were equally likely, what's the chance the first scoop is chocolate? Okay, so everything's equally likely, and we want to know what's the chance the first scoop is chocolate. Well, if the first scoop is chocolate, these all have first scoop chocolate. So there's 5 cones that have first scoop chocolate. That's out of a total of 20. So if they're all equally likely, that means we've got 5 are first scoop chocolate out of a total of 20, making 25% chance that the first scoop is chocolate. A different question is, what's the probability that any scoop is chocolate? So notice now, these are all chocolate cones, and these are all chocolate cones. So it would be tempting to say that we have 4 of this type and 5 of this type, making 9 total, and you have 9 out of 20. But in reality, if you actually count these, we have 1, 2, 3, 4, 5, 6, 7, 8. There's only 8 because this cone would have been double counted using the row and column total. So there's actually 8 chocolate chocolate cones. So the answer to that would be 8 out of 20. So we have a 25% chance of first chocolate and a 40% chance of any chocolate. So I would contend that the answer that 40% of the cones have chocolate in them is not something that would have been easy to just infer from reading the problem. The fact that we built the contingency table, carefully calculated all the possibilities, and then counted them, being sure to ignore duplicates, was actually an efficient and effective way of getting an accurate estimate of that number, or an accurate conclusion on that number. That would have been tough to do using a different method. So contingency tables are powerful both for listing possibilities but also for calculating probabilities. So here's another example. This is a situation where you have someone doing a purchase or visiting an electronics retailer. If they go through the door, they may or may not buy a plasma screen television, and they may or may not buy a DVR. And so if we observe 300 people go through the door, we then can start thinking about all the different possibilities. So of the 300 people, 220 did not buy a television, while 80 did. Well, 108 bought a DVR, 192 did not. And so you could think, well, this is a certain fraction of the total here, and this is a certain fraction of the total here, and this is basically 2/3, and this is basically 2/3. And so you would think, well, maybe this is 4/9, and so on. But the reality is, these individual cells on the interior don't have to match the proportions here. So, for example, it could be the case that no one buys a DVR who buys a plasma. Maybe that's just too much money to spend in one visit, and this cell has a 0. Or maybe it's highly likely that you buy a DVR if you buy a plasma because you're planning on watching more television and you want to be able to record it effectively. So this may be more than the proportion you'd expect. And so these individual cells tell a story about how plasma and DVR interact in the lives of consumers. And we can ask simple probability questions just like we did with the ice cream scoops. So what's the chance that a person buys a plasma television? Well, there's 80 plasma buyers out of 300 total. That's a marginal probability of purchasing plasma. The marginal probability of purchasing a DVR is 108 out of 300. And now we can also extend this idea to think about, well, what's the probability that I purchase both a plasma and a DVR simultaneously, both of those things? Well, that's 38 out of 300. So if we think like that using a contingency table, we've actually extended into the realm of joint probability, where we think about doing two things at once. So if I think about a situation where with my left hand I roll a 6-sided die, and with my right hand I flip a coin, we can ask certain probability questions like, what's the chance of 2 or smaller? Well, these 4 are 2 or smaller out of 12. 4 out of 12 is 1/3. Tails. 6 are tails out of 12 is 1/2. 3 or smaller and tails. So 3 or smaller would be these 6, but tails would restrict it to just these 3. So that would be 3 out of 12, or 1/4. 1 or 6 and heads. So 1 or 6 would be these 4, but heads would be restricted to 2. 2 out of 12 or 1/6. And then 1 or 6 or heads. Right? So 1 are these 2, 6 are these 2, and heads are these 6. So 1, 2, 3, 4, 5, 6, 7, 8. That would be 8 out of 12, or 2/3. So there's lots of different kinds of probabilities we can quickly calculate or assess once we've built a contingency table. So now we're going to do an application of this in terms of a convenience store. So this particular convenience store is interested in whether selling milk as a loss leader will result in increased consumption of higher profit margin items. So this like snacks. So if you come in and you buy some milk, are you more likely to buy snacks while you're in the store? So they did an observation of 400 people. So now we've got some data, and I'm going to ask you to tell us some information from the contingency table. So of 400 people who shop at a convenience store, 300 buy milk, 80 buy only snacks, and 240 buy snacks. Right? Just to be clear, that means of the 240, some of them bought milk and some of them did not. It's agnostic about whether or not you bought milk, but 80 bought only snacks and therefore did not buy milk. How many buy milk and no snack food? So we've got some counts of the various categories. So go ahead and make a contingency table and figure out how many you think bought milk and no snack foods, and then we will solve it together and see how you did.